Hello everyone, welcome back. So today we have same type of questions, that is D and F block elements. We are revising D and F block elements through question and answers, where we have taken into account the previous year CBSE questions. Okay, so today's first question that we have discussed in our previous video as well. Metal-metal bonding is more extensive in the 4D and 5D series of transition elements than the 3D series. Explain. So, as we go down the group from 3D to 4D and 5D, atomic size increases. Atomic size increases. And at the same time, metallic character increases. That means elements are more, means electrons in the elements are more available for bonding, more involved in the bond formation. That's why in 4D and 5D series, metal-metal bonding is more extensive than in 3D series. This is the simple reason, that as metallic character increases, metal-metal bond is more easily formed, because electrons are more available for donation, or we can say bonding. Okay, next question. Why does Mn3 plus, in Roman we write it like this, oxidation state of manganese 3, undergo disproportionation reaction easily? So question is, why does Mn plus 3 undergo disproportionation reaction easily? If we compare Mn2 plus and Mn3 plus, see, Mn2 plus is 3D5 and Mn3 plus is 3D4. So on and what about Mn4 plus? It is 3D3. Okay. So in aqueous solution, see, Mn3 means oxidation state is in aqueous solution. So Mn2 plus is more stable than Mn3 plus, because it is exactly half filled configuration. So E naught value of Mn3 plus to Mn2 plus is positive, okay, plus 1.57. Therefore it undergoes disproportionation, okay, because Mn3 plus is less stable or unstable as compared to Mn2 plus as well as Mn4 plus. So Mn2 plus undergo disproportionation, Mn3 plus undergoes disproportionation to give Mn2 plus along with Mn4 plus. Okay, so 2 moles of Mn3 plus changes into Mn2 plus and Mn4 plus. So very good evening to all of you, Saad, Ashish, Harshil, Praharsh, Varun, Kashmira, Charitre. So this is question number 2. Now question number 3. Question number 3 is, how would you account for the following? First is, many of the transition elements are known to form interstitial compounds. Many of the transition elements are known to form interstitial compounds. Second part of the same question is metallic radii of third transition series. Third transition series means 5D series. Of third series of transition metals are virtually the same as those of the corresponding group members of the 4D series. And third is lanthanoids form primarily +3 ions, that you know all, while the actinoids usually have higher oxidation states in the compounds, like +4 or even +6 being typical. So these are the three parts of the question number 3. So tell me, why many of the transition elements are known to form interstitial compounds? Yes, beta. Because, yes, anybody who can answer it? To form interstitial compounds. Because transition elements are large enough. Yes, very good. Transition elements are large enough, so when they form the lattice, the small elements like carbon, nitrogen, hydrogen can be trapped in the interstitial sites, okay, in the lattice of the compound. That's why they can form interstitial compounds, okay. So you can write that transition elements are large enough in size so that when they form the metallic lattice, the voids, or we can say empty spaces or interstitial sites can accommodate small sized elements. That's why they can form interstitial compounds. Second question is metallic radii of third series of transition metals are virtually same as that of the corresponding group members of the 4D series. So for this you can write it is due to lanthanoid contraction. Because of lanthanoid contraction, second and third transition series have almost similar size. So reason being due to lanthanoid contraction. Very good Sahil. Now third question. What about third? Lanthanoids form primarily plus 3 ions, while actinoids usually have higher oxidation states in their compounds. Because in actinoid series, yes, tell me. Because in actinoid series 5F, 6D and 7s orbitals, they have comparable energies. They have comparable energies, okay, and that's why electron in these orbitals can take part in the bond formation, okay, to show higher oxidation states. As all have say comparable energies, all are treated as valence orbitals. That's why they can easily participate in the bond formation, and that's why they can show higher oxidation states. Adarsh Singh, beta, inorganic, to study it easily, you can go for question answer round. Better to go for question answer rather than looking at the theory. Better to go with question answers, okay, and just see what type of questions came in previous years, okay. Right. Okay, now question number 4. Why do most of the transition ions exhibit color? Why do most of the transition metals ions exhibit color? In aqueous solution? Yes, beta. Why do most of the, very good, Sahil, right answer. Reason being, because they have partially filled, in most of the cases, they have partially filled d orbital. That's why dd transition is possible. So this is the reason, because they have partially filled d, not vacant. Harshil, you should write because they have partially filled d orbitals, okay, that's why dd transition is possible. So they are colored, okay. Next question. Wait. Why Mn3 plus is a good oxidizing agent? Mn3 plus is a good oxidizing agent. Give reason. Yes, what is the reason? Why Mn3 plus is a good oxidizing agent? So Mn3 plus is a good oxidizing agent because you can write E naught value of Mn3 plus to Mn2 plus is very high. This is the actual reason. As a result, Mn3 plus can be easily converted into Mn2 plus by accepting electron. This reaction can be easily taken place. Mn3 plus aqueous plus electron to Mn2 plus aqueous. That's why it is a good oxidizing agent. Yes, you can write Mn2 plus is more stable in aqueous solution than that of Mn3 plus. But if you write about its standard EMF value, that is the proper reason. Okay, Sahil, you can write both. Okay, next question. E naught of M2 plus to M values are not regular for first row transition metals. That is 3D series. So tell me the reason. E naught of M2 plus values are not regular for first row transition metals. Yes. What is the proper reason for that? Can you guess? Yes, beta. Any guess? Hello everyone, tell me. Titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Saw the lengthening and contraction everywhere you can fix it. Yes, you can write due to the not ionization enthalpy only, due to different heat of atomization. See, when you have that value, see M solid, that is turned into M2 plus aqueous plus 2 electron, right? So first of all, M solid is converted into M gas, then M gas into M2 plus gas, then M2 plus gas to M2 plus aqueous. This is the proper way to represent the EMF. Okay, so M solid first sublimation enthalpy means enthalpy of atomization is used, then first and second ionization enthalpy is used, and the third one is hydration enthalpy. These are the three things involved. Okay, while determining E naught value. Okay, so they say in titanium, see for scandium 2 plus does not exist, so there is no need to write for scandium. Okay, but for titanium it is minus 1.63, for vanadium it is minus 1.18, data is given. Chromium it is 0.90. See, there is a decrease in negative value. Okay, but as we reach manganese, it becomes minus 1.18 volt. Then again minus 0.44, minus 0.28, minus 0.25, and then it becomes plus 0.34, and then minus 0.76. So proper reason for it is due to the variation in ionization enthalpy, enthalpy of hydration, enthalpy of atomization. Yes, Sahil, you are right. You can write all the things belonging to or which determine the factors which affect the E naught value, that is the enthalpy of atomization, first and sum of the first and second ionization enthalpy, okay, and enthalpy of hydration. Okay. So, proper reason is, yes, what is the proper reason? Like Sahil wrote in the comment box, chat box, that is, it is due to variation in the values of, due to variation in the values of enthalpy of atomization, enthalpy of hydration and ionization enthalpies are not quite regular. Okay, that's why due to the variation in these values, the value of E naught M2 plus M, they are also not regular. Okay. Now next question. Although fluorine is more electronegative than oxygen, although fluorine is more electronegative than oxygen, the highest oxidation, highest fluoride of manganese is MnF4, while the highest oxide is Mn2O7. What is the reason? See, fluorine, you know, more electronegative than oxygen. So obviously with fluorine, metal is more prone to lose electrons than that of oxygen. But even then, see, with fluoride, it can form only an MnF4, that is up to +4 oxidation state. But with oxygen, it can go up to +7. What is the reason? So, simple reason is that oxygen has the ability to form multiple bond. Very good, Sahil. Oxygen has ability to form multiple bonds with transition metals. Okay, but fluorine cannot. Cannot do so. This is the simple reason, that oxygen has the ability to form multiple bonds. That's why manganese can form only this type of structure, but in Mn2O7, you can write it like this. Mn2O7. Okay. Now question number 8. Yes, what is lanthanoid contraction? just define. So lengthenoid contraction is simply steady decrease in size among lanthanoids as atomic number increases. Okay, so that's why that is called lanthanoid contraction, and due to lanthanoid contraction size decreases along the lanthanoid series. And name an alloy which contains some of the lanthanoid elements. Yes, decrease in radii along the series as atomic number increases. Now tell me the name of the alloy which contains some of the lanthanoid elements. Yes, this name is given in the book. Wow, very good beta. Mixed metal. Mixed metal, and mixed metal is an alloy. It contains around 50% cerium and 40% lanthanum, okay, along with other elements. Okay, good. Okay, question number 9. Name the transition metal which shows maximum number of oxidation states in the first transition series that you all know. Yes, tell me. Name the metal, transition metal, okay, which shows maximum number of oxidation states. In the first transition series. Yes, beta. In the first transition series, which elements show maximum oxidation state? Respond fast. Very good. Manganese, because in manganese it has maximum number of unpaired electrons. Okay, so it can show oxidation state from +2 to +7. Okay. Yes, next question is also very simple. Which metal of the first transition series exhibit +1 oxidation state most frequently and why? Very good, Saad. Yes, tell me, which metal of the first transition series exhibit +1 oxidation state? Most frequently and why? That you all know. Very simple question. Very good. Copper. And why is it so? Because copper in +1 oxidation state has electronic configuration 3d10, that is fully filled electronic means it require noble gas configuration, because copper is 3d10 4s1 and copper 1 plus is 3d10 4s0. So it acquires stable electronic configuration because it shows stable electronic configuration. Good, Ashish. Right. Next question. Name, 11th question. Yes, name two elements which shows only +3 oxidation state. Only +3 oxidation state. Two elements which can show only +3 oxidation state. Name two elements which shows only +3 oxidation state. Only +3 oxidation state. I am writing next question, you will answer it. Which of the following cations are colored? You will answer the previous one. Name two elements which shows +3 oxidation state only. Chromium? No, beta. Wrong answer. Chromium can show +6 as well. Iron can show +2 as well as +3. Europium? No, beta. It can show +2, +3. Scandium. Is there any other oxidation state other than +3? And lanthanum. These are the two elements which has only +3 oxidation state. Only. See, what name two elements shows only. Sorry, I will forget to write it. But which shows only, I forgot to write it, only. Which shows only +3. Okay. So that is scandium and lanthanum only. Which of the following cations are colored in aqueous solution and why? Ions are scandium 3+, vanadium 3+, titanium 4+, and Mn 2+. Yes. So, to identify which of the following cations are colored in aqueous solution and why, first of all, we should write their electronic configuration. So, scandium atomic number is 21. It has configuration of argon only. It is 3D 0. And vanadium 3+, Z is 23. So, it is 3D2. Very good, Harshil. And titanium 4+, that is Z is 22, and it is again 3D0. And Mn2+, Z is 25, argon 3D5. So, obviously, scandium and manganese, these two ions, vanadium and manganese, these have partially filled 3D orbitals. That is why DD transition is possible, and that is why they are colored. But scandium and titanium 4+, scandium 3+, and titanium 4+, they have no d electron. Okay, that's why they are colorless. They are colorless. In first case, there is dd transition possible. dd transition is possible, but here dd transition is not possible. Next question number is 13. Okay. Question number 13. Question number 13 is, why do zinc, zirconium and hafnium have almost identical size? Yes, tell me. Why do zirconium and hafnium have almost identical radii? Very good. It is because of lanthanoid conflict. Yes, beta, buffer topic is very important. It is due to lanthanoid contraction. Reason being lanthanoid contraction. Okay. See, zirconium, niobium, hafnium, tantalum. Okay. So, zirconium and hafnium, niobium and tantalum, they have almost same size due to lanthanoid contraction. This is question number 13. Now, 14. Why are cadmium salts white? Why are cadmium salts white? So, you know, cadmium 2 plus, it is 4D 10, which means 4D orbitals are paired. Hence, there is no DD transition. There is no DD transition, and that's why salts are colored, because they have fully filled d orbitals. Very good, Saad. No DD transition, and that's why they are white. Next question. Zinc shows only +2 oxidation state in its compounds. Explain. What is the reason? because after losing 2 electrons, see zinc is argon 3d10 4s2. So after losing 2 electrons, it becomes 3d10. It has fully filled electronic configuration, more symmetrical, therefore it has extra stability. So now it has no tendency to lose more electrons. It has no tendency to lose any more electrons, and that's why it shows only +2 oxidation state in its compounds. Very good. It is difficult to remove electron from d orbitals because it is stable. Yes, copper 1 plus is colorless and copper 2 plus is colored. What is the reason? Copper 1 plus is colorless, copper 2 plus is colored. Reason? Same reason, copper 1 plus is 3d10 while copper 2 plus is 3d9. So copper 1 plus as it is 3d10, because of fully filled d orbital, no dd transition is possible. While here in copper 2 plus it has partially filled d orbital, dd transition is possible. So this is the reason that copper 1 plus is colorless and copper 2 plus is colored. Right? Okay. So tell me, why is enthalpy of atomization is lowest for zinc in 3D series of transition elements? Why is enthalpy of atomization is the lowest for zinc? In 3D series of transition elements. Yes beta bolo. Why is enthalpy of atomization is the lowest for zinc in 3D series? Yes. Because of atomic size? Is it so? It is because zinc has no unpaired electron. Zinc has no unpaired electron. As a result, DD interactions are negligible, or we can say DD interactions are negligible, or we can say metallic bondings are weak. Okay, that's why it has lowest enthalpy of atomization. Yes, Sahil, very good. More number of unpaired electrons, more metallic bonding, means more stronger metallic bonding and more enthalpy of atomization. For zinc, there is no unpaired electron, that is why metallic bonding is weak and therefore enthalpy of atomization is negligible, is low, we can say, okay, because of fully filled, or we can say symmetrical electronic configuration. It has weak metallic bonding. Okay. Okay, so that's all for the day. We will continue in the next class with the same topic, same chapter, Sony. Okay, beta. So, bye for now. I am signing off. Okay. Okay. Bye, beta. Bye.